project is about trying to figure out what are some of the core base units of the zebra-finch language. If there is kind of a sophisticated language where the base aspects, base lexical items that come together to form the zebra-finch grammar structure. So we're going to use some traditional machine learning classification models, a deep learning classification model, as well as generative adversarial networks. We'll talk more about that. First, we have our data set. We've got 3,000 recordings of their vocalizations, about a second each, manually annotated by some research domain experts with the call type. So we've got begging, long tonal distance, etc. And then for our feature set, we created this kind of hand-engineered matrix comprised of some core spectral feature properties. We figured out what are the ones that we liked best by training our models on a bunch of different ones, employing dropout randomization of different features to see which ones led to the best predictors. We have spectral flatness, contrast, tempo. Then we also have these MEL spectrograms. This is what we gave to the CNN, just like the images of these, and you can see that we've got the frequency of the sound over the time domain with the intensity of the amplitude, but then scaled for the human perception scale, which is also the same as, or very similar to the zebra-finch audio perception scale. Okay, so for our classification models, we've got a couple. So we've got multinomial, random forest, LDA, CNN. So for a multinomial, first we trained this on the spectral features matrix, then we went and retrained it on the MEL coefficients. We'll talk a little bit about why, but we use LT regularization for this model to prevent overfitting by penalizing super high weights. For random forests, we train this on our spectral features matrix and enforce min number of examples required to have a split, and then also the max depth to prevent overfitting. LDA, we kind of got a hint that this might be a good model based on another research paper that showed that it might be a good predictor of call type. It's like GDA almost exactly, except that you learn a single covariant matrix for all classes. For convolutional neural network, so it's a type of deep learning network. It's kind of like the core of this is the convolutional layer, where you have this filter or this kernel sliding across your input, creating a feature map by multiplying the portion of your input that falls under the feature by the weights of the feature, the weights of the filter by the weights of the kernel to create the feature map. So you have the weights of the kernel by the input equals the feature map, and with multiple convolutional layers, you can learn progressively more intricate details or intricate features of your image. And so those are our core classifiers, and we have our generative adversarial network set up. So again, you have these two models competing against each other in a zero-sum game. So a generator and a discriminator. So the generator wants to create fake data that resembles the training set enough such that the discriminator gets tricked, and the discriminator wants to not get tricked. And so in this case, we're using an extension called WaveGAN that allows for it to process raw audio data. So the generator is taking a noise vector, creating some raw audio data. The discriminator is taking some raw audio data and giving the likelihood that it is real. And so now the loss function for the generator is just like the negation of the probabilities that the discriminator assigns to its data being real. And that way you can see that it loses more when the discriminator thinks its data is not real, so assigns lower probabilities. And it loses less when the discriminator thinks its data is real and assigns higher probabilities. So that's over here. And then for our loss function for a discriminator, it's the Wasserstein distance, or the Earth mover's distance, between the probabilities it's assigning to the generator's data being real and the probabilities it's assigning to the discriminator's data, to the real data being real. So this is a sample. It will get a sample of real training data. It will get a sample of what the generator's creating, and it will assign probabilities to the two, each one of them being real, and the Wasserstein distance between the two is the loss function. When this is higher, when it thinks that the generator is real, it loses more. When it thinks that the discriminator is, when it thinks the real data is real, so the discriminator thinks the real data is real, it loses less. And now we know, so now in this current setup, we're able to create this this setup where the generator, the discriminator and the generator make each other progressively better. The generator is able to create realistic content. It maps to this noise vector somehow. We don't know how, and we really can't understand or the relationship or how to control it. So then here comes InfoGAN. InfoGAN adds a Q network. The Q network basically says, first of all, we modify the generator, so now it's taking input of the typical latent noise plus the latent code. The latent code is something we can manipulate, and the Q network's job is to guess the latent code from just the generator's output. So now the generator has to both create believable content that can trick the discriminator, as well as create content correlated to the latent code in some ways, such that the Q network can take that output, guess the latent code. All right, so a quick look at our classifier results. We held out like 40 to 50% of our data to prevent overfitting, because it was super important in our case. And so these are our accuracies. We found that the CNN performed super well. I guess that the mil spectrum captured a lot of the core properties that correlate to call type, and that the CNN most efficiently was able to find relationships between that and the call type. And then now we're looking at the effect of manipulating latent code. So now in InfoGAN, when they introduced that paper, they trained it on the MNIST data set, and they had like handwritings of various different drawings of or handwritings of digits between 1 to 10, and a latent code that allowed for 10 classes. And they found that when they went and manipulated that latent code, every latent code mapped to a certain digit, and they can control what digit was outputted by the latent code. And so the idea here is that maybe the latent code will map to some lexical items. And so first we're going to look at the class, the impact of the class when we manipulate that latent code. So we gave different latent codes with the same noise vector to the generator, got the output, and then used the different models to guess the class. We found the convolutional neural network really was seriously confident that these were nesting calls, right? Very, very confident. And we retrained our multinomial logistic regression to use the MEL coefficients, because maybe that was really important to figuring out call type, and the CNN was just not very, very confidently wrong. And it turns out, yeah, our generator had suffered from mode collapse. Mode collapse is when your generator gets really good at creating a small range of output, a small range of output that it can fool the discriminator on. It steps outside of that range, and the discriminator can immediately know, hey, you're fake, you're inauthentic, and so it's not really motivated to try creating outside of that range. So this is one of our first conclusions, that when going to a space where you can't easily perceive the class, come in with good classifiers, so that way you can figure out whether you're suffering from mode collapse, etc. Second thing is, then we looked at what the effects of manipulating latent code on spectral properties. We found that there was a relationship between spectral properties and latent code, and that makes sense. If the class is held constant because of mode collapse, then the next thing that you have that you can manipulate, that you can correlate to the latent code, such that the Q network can get some sense of what that is spectral properties. And we measured the difference based off of the L2 norm of spectral features matrix, MEL coefficients matrix, etc. TLDR, our conclusions are, this has a lot of potential in the future. We want to figure out if we can use reinforcement learning to learn the optimal number of encoding bits for the latent code, because we think that has a different effect on, or a different number of latent codes per different number of lexical items. It equals the different likelihood that that latent code is going to map to those lexical items, and we talk about that a little bit in the paper. That's it. Thank you so much for listening. Sorry if this went a lot over. Bye.